Alright, you are most welcome once again. As and Soak as usual, we want to continue with this. In this case, last time we left when we wanted to look at an example under division. If z1 equals 2 plus I and z2, this is z1 and z2 equals 4I plus 1. That's the thing. We want to see that we want z1 over z what? z2. This is division. So this is z2 plus I over 4I plus what? Plus 1. You can put in the other usual way of rearranging. You begin with this one as you know, but even if you do this one, so long as you know that this is the imaginary part and this is the real what? Real part. Such that when you are changing the sign, you change the one of the imaginary part. You should not cram me that we change what is here. We change the sign of the imaginary part. In this case, we shall have 2 plus I over 1 plus 4I. In this case, this is 1 minus 4I. We say that you get the conjugate and you multiply it by up and down. So when you are here, you open the bracket. 2 times that is 2. 2 times that minus 2 times 4 is 8, but I. Then I times that is plus I. Lastly, I times negative 4I. It is already minus, but there is I squared, of which we shall have a positive 4. So in this case, we are having difference of 2 squared, that is 1 squared. Then we say that this one will be 4 plus 4 squared, according to what we said last time. If you are finding challenge with this thing here, you try to review the previous lesson whereby we looked at this thing here, division, and we saw how the plus comes. How does you come here on the minus, because this is the difference of 2 squares. You remove this square and also a square here, and you see how you get this. So in this case, we are saying that this is 2 plus 4. Or if you can't get this one directly the other way, open these brackets. Open these brackets here and multiply everything. You will end up with something of that form. So this is 2 plus 4, that is 8. 6, sorry. 2 plus 4 is 6. Then minus 8 plus 1, that is 7 what? 7I. And we are saying that if it is 7I, we are having 1 plus 4 squared is what? Is 16. So 1 plus 16. So we are having 6 minus 7I, and this is over, that is 17. So we split 6 over 17, then minus 7 over 17I. So we see that this is our Z1 over Z2. It has the real part, 6 over 17, and the imaginary part, negative 7 over 17. That is it. Now, today's task is all about looking at what we call a modulus of complex number. We want to look at modulus of a complex number. So if we want to look at modulus of a complex number, what shall we do? We shall have the first thing. We shall have a complex number, maybe z what? Z equals x plus yi. We shall have what we call a complex plane. So we have two things, so people confuse them. This is what we call the real axis, and this is imaginary what? Axis. In Cartesian planes, we have x-axis and y-axis. Those are the axes we are having. That's in Cartesian plane. Now, this is now complex plane, whereby we shall have the real axis and the imaginary axis, because the complex number has real value and the imaginary part. Real part and imaginary part. That's why we shall have real axis and imaginary what? Axis. Where there is x-axis, we have real axis, and where there is imaginary axis, where there is y-axis, the other side, we have imaginary axis. Don't confuse them. So this is what we call a complex plane. When it is like this, it is called a complex plane. Now, there is a possibility this complex number can be written as x, then y, whereby it can be written in coordinate form. In that case, this is x and y, x, y. So x is the coordinate of the x-axis. If this is x and maybe y is here positive, you plot this now point now. It is there. So a complex number, we shall have it like that. Sometimes people put an arrow and this is now your z as the complex number in that case. When you do it like this, it is now what we call an Agandi diagram. This is now an Agandi diagram. The other side we have Cartesian diagram. Now this side is have a Gantt diagram. Before drawing the complex number, that it is called a complex plane. But now after including a complex number, that it becomes an Gantt diagram. Because if you want, you can go and read the history of Gantt and say that now it makes an angle here that we shall look at and we see what it says. In that case, we know what is happening. Now we are having from here up to here is y, and from here up to here is what? X. This is what? R. So from here up to here is what we call the length of the complex what? Number. From here up to here, and we always denote it as R. Now in this case, what do we do? We call it modulus. Some people call it length. Some people call it magnitude. Some people call it magnitude of the complex number. So how do you get it? If a complex number is z, we denote it by z bar. This one we can call it what? R. How do you get length here? In this case, here we apply Pythagoras what? Theorem. We apply Pythagoras theorem as we want to say right now. We said we apply Pythagoras theorem. So in this case, when we apply Pythagoras theorem, we shall have x squared plus y squared equals r squared. So our r will be equal to x squared plus y squared and the root. So this is the one we are calling z bar, and this is what we are calling modulus of the complex number, or length. Sometimes we call it magnitude. So this is the one we shall have in this case. We always put the answer as units in that case. So that's what we are having. An example. Someone can look at an example here and say that if it is z equals 1 plus maybe I, you say that z bar will be equal to x squared plus y squared square root. This one, when you compare it, your x is 1 squared, then your y is what? Is 1 also squared. So you say that this is 1 plus 1 and this is 2, but root. Always put units since it is what? Since it is length. This is what we shall be having. So any complex number, you do it like that to get the what? The modulus. In this case, we shall look at what we call the argument. There is something called the argument also. Argument of a complex number. Shall also look at argument of a complex number. When we are looking at argument of a complex number, what do we do specifically? We look at this. If you have any complex number, for example, you can draw another Gantt diagram. This is x plus what? Y. So the Gantt diagram, as we said, we have an Gantt diagram whereby you first draw the complex plane with the real axis, and then this is imaginary axis. So you have x here, you have y as we saw above. When you plot this point here, this is xy. So we have this angle here that we make with the what? The positive real axis or the horizontal. So in this case, this one here, the angle that the complex number makes with the positive real axis is what we call the argument. At this level, we have what we call the principal argument. Here you come and you get this angle. You say that the tan of theta equals the opposite over adjacent, of which our opposite is y over adjacent, which is x. So theta because tan inverse, some people call it tan arc of x, y over x. The angle you get here will not be necessarily the what? The principal argument. For us, we are interested in the principal what? Argument. And we always mention the word that the principal argument is unique. You will get very many angles here. For example, you may draw this complex number when it is here, like this, and you'll be getting this angle here. Does it mean that it is the argument? You draw a complex number here, then you have this, you can also get this angle. The complex number may be here, and you have this what? This angle here. So expect all of those things here. So how do you get the principal argument that we use, the one we are interested in? Your work is to get this angle here with the horizontal, this angle here with the horizontal. Now, what do we say? When you are in this quadrant here, take the angle you get as the argument. When you are in this quadrant here, you call it negative angle, to be negative angle. Now, when you are here, we call it 180 negative, then plus the angle. But when you are here, you get 1 pi minus what? Minus the angle. Why? We always say that the theta that we talk about lies it ranges from negative pi and it goes up to positive pi. Negative pi is not included, but pi is included positive. The angle that lies with negative pi is 180 degrees, negative 180 degrees, also pi. Generally, pi is 180 degrees. So the principal argument lies within this what? And it is unique. It is only 1 for any complex number. When you calculate, it will only be 1. So if you get the answer when it is not lying in this way, that is not the principal argument. We are interested in the principal what? Argument. In this case, we always say that this one that you are getting here is what we call the what? This angle here can be the argument. For example, it is in this one, in this quadrant. So how do you do? When you are in this one, you add. When you are in this one, you do subtract. Whether the imaginary part is negative, we don't mind on the negative. The negative just tells you where the complex number is. For you just come, for example, if someone tells you that z equals maybe negative 1, then minus 4i, just come on the real axis, and we also have imaginary what? Axis. You come and have negative 1, then negative 4. So this one is telling that the complex number is in this what? This class. So for us, we want this angle here. First get this angle, whereby from here up to here is 1, from here up to here is 4. So the y is 4, tan arc. Y is 4, and your x is what? Is 1. Don't mind about the negative. The angle you get is this one. So after, we are interested in this angle from here up to where? After, because everyone knows in trigonometry that when you are measuring angles in the clockwise direction, those angles are negatives. But if you are measuring them in the anti-clockwise direction, they will be what? Positive. Now, if you measure like this, and you measure like this, you see that this one goes beyond 180 if you move from here up to here. Now, this one doesn't go, so we take this one as the what? The angle. That's why we say that in this one, get negative pi plus what? Plus the angle you are getting in that case. When you are here, just take it, but it will be what? Negative. So generally, what are we saying? First thing, our angle will lie in this one, the argument, principal argument. Secondly, the principal argument is unique, and it is only what? It is only 1. Number 3, we always measure the angle from the positive real what? Axis. We measure the angle from the positive real axis, and we make sure that it doesn't go beyond this what? Beyond that range. Then the last thing is that the angle is transferred to radian. The argument is recorded in what? In radian. And everyone knows how to record the argument. That if the argument is theta, then it will be theta in degrees times pi over what? 180. The answer you get, it will be in radian, and it must remain with what? Our pi. We want to look at an example here in this case, and you see an example. It is this one. Example. We can have z equals negative 1 minus I. There is that one here. Someone can have that one. Someone can have z. Maybe z equals. You can have. Let us assume someone can have 1. you can also get the argument of that. Someone can also have z equals maybe negative what? Negative I. They are all there. So for me, I will do this one here. Someone can do that one there, and you see the answers you get. But I told you we don't include negative pi and pi in that case. I'll draw something here that I can. We always get these angles after drawing this. Don't make any mistake to draw to get the angle minus drawing this one. So 0 is our, because this is 0 minus I. So if it is 0 minus I, we shall have so negative 1 down. So 0, negative 1 is here. So if it is 0, negative, because this one the same as writing the point, 0, then negative 1. So 0, negative 1 is here, of which if you see this one, you plot. So this is our complex number, so it will move from here. You can't move from this side up to here. So we just, so this one is 90 what degrees when you move from here up to here. However, we always say that this one is in the negative direction and clockwise direction. Therefore, this one will be what? Negative. So we shall say that in this case we are saying theta equals negative what? 90 degrees. You transfer this one to negative 90 times pi over what? Over 180. And we shall have negative pi over what? Over 2. This one becomes our what? Our principal argument in what? In radians. So that's how we always do these things, as we shall look at more and more in that case. At the moment, we shall pause from here. We shall continue from here when we come to the next what? The next part of calculating, putting the thing in argument. Expect things like the conjugate of a complex number, polar form of the complex number when we come what? When we come back. I wish you the best. Asante Kusoka is my name.